Hello, this is On the Spot STEM, and today we will be tackling 2014 Aime I problem number 14. And in this problem, we have to find the largest real solution to this equation. Now, the first thing to notice is that this equation is actually a polynomial of degree 6, and this can be more easily seen when we try to clear the denominators by multiplying both sides by x minus 3, x minus 5, x minus 17, and x minus 19. And because each of these denominators is somewhere within this product, they'll all go away. But we also have to multiply the other side by x minus 3, x minus 5, x minus 17, and x minus 19. And then we can clearly see that we'll have degree 3 polynomials here because this is degree 4, but we subtract a degree because of the denominators being cleared. But here, there are no denominators in the first place, so we don't need to clear any of them. And we can clearly see that this is of degree 6. And whenever we see a polynomial with a degree of higher than 2, usually our first instincts are to find easy solutions with rational root theorem or to take advantage of symmetry, because with higher degree polynomials, there are explicit formulas to find the roots of a cubic or a quartic, which are degree 3 and degree 4 polynomials respectively, but there's no formula for anything higher than that. And even though there is a formula, they are horrendously messy, so you're not expected to use them. So there has to be some sort of trick that we can use to find the roots of this polynomial. So if we attempt to use rational root theorem, we will need to find the constant term, and we'll also need to find the leading coefficient. And because the only degree at maximum on this side is 3 because of the denominators being cleared, we had to look at this side where there's a degree 6 term, and clearly we can see the leading coefficient is 1 by x squared times x times x times x times x. However, finding the constant term will be quite messy because we'll have to multiply large numbers out, like 5 and 17 and 19, and that can get messy. And even if we find a root, we'll have to divide it into the polynomial, and that can also get very tedious. So maybe rational root theorem is not a good idea, and maybe we should try the second approach, which is to take advantage of symmetry. So now we should try to search if there's any symmetry within this equation. And something I noticed is that 3 and 5 are 2 apart, but so are 17 and 19. And 19 and 3, those add up to 22, but 5 and 17 also add up to 22. So there seems to be some symmetry around 11, and there's an coefficient of negative 11 on this side, so that gives us even more reason that there could be some symmetry around 11 with this polynomial. So we should try to make a clever substitution to take advantage of the symmetry. And the reason why taking advantage of symmetry is good for higher degree polynomials is, say like you had a polynomial x to the fourth plus ax to the third plus bx squared plus cx plus d. And sometimes if we take advantage of symmetry, we'll get a polynomial in the form x to the fourth plus p times x squared plus q. And while this is still a fourth degree polynomial, it's a quadratic with respect to x squared, and that's much easier to solve because if you Google the quartic formula, it's horrendously messy and extremely long and extremely impractical to memorize. And because of this, even though this is a 6th degree polynomial, taking advantage of symmetry can help us find easy roots or can help us understand more about this polynomial. So we see that the x minus 5 and x minus 17, those are centered around x minus 11. So maybe x minus 11 is an important substitution to make. So let's call this y. And then we just substitute this into the equation, but let's solve for x. X equals y plus 11. So that means this is y plus 8 plus 5 over y plus 6. And then this is plus 17 over y minus 6 plus 19 over y minus 8. And we can easily combine these denominators because y plus 6 times y minus 6, this product comes out to y squared minus 36, and we lose the linear term, which makes it, again, easier to solve because we took advantage of the symmetry and we could try to solve it as if it were quadratic, which is a degree lower. And usually lowering the degree of a polynomial is very difficult, and this is one of the few strategies that you can use. And then we have to simplify the right-hand side, and we notice x times x minus 11 minus 4. And since x minus 11 is y and x is y plus 11, this comes out to this. So now that we capitalized on the symmetry and realized how powerful it is, let's combine the terms with the matching denominators, which they aren't the same, but they're corresponding. So we have 5 times y minus 6 over y squared minus 36 plus 17 times y plus 6 over y squared minus 36. And then with this combined, we get y squared minus 36 with a 22y plus 72 up top. And then if we combine these two, we get a y squared minus 64 on the denominator. But we'll also have a 22y plus 16 times 8 is 128 equals y squared plus 11y minus 4. And we may be stuck here, but one thing to notice is that this 36, that's half of 72, and this 64, that's half of 128. And wishfully thinking, we want to cancel out that 128, then maybe we could divide through by y. And to get that, we need a plus 2 for both of these, because negative 36 times 2, that is negative 72, and that'll cancel out the 72. And here we have a negative 64. Multiply that by 2, we get negative 128. That will cancel out the 128. So we want to add 2 to both of these. And luckily, we have a 4, so we can distribute this 4 to these two terms and hopefully cancel out these 72, this 72 and this 128. So we'll have 2y squared minus 72 over y squared minus 36 plus 22y plus 72 over y squared minus 36. And then we see that the 72's cancel. And then likewise, we'll have 2y squared minus 128 over y squared minus 64 plus 22y plus 128 over y squared minus 64. And then we'll see that these 128's cancel. So, and this is all equal to y squared plus 11y. And note that we got rid of the 4 because we distributed it to these two terms just to get rid of these constant terms. And now we can combine all of this into a one-line equation just so that it's easier to see. And now this equation looks a lot simpler than this, even though it's still a 6th degree polynomial. So it seems like taking advantage of the symmetry was a very powerful and big step forward because we made a lot of progress and we made the polynomial look a lot easier, and it's only going to get better from here. So looking at this equation, we notice that y squared plus 11y can be factored out from each of these terms because this denominator can be written as 2 times y plus 11 over y squared minus 36. And we can do a similar factorization for this term. 2 times y times y plus 11 over y squared minus 64. And the right-hand side can be factored as y times y plus 11. And then we notice that we can divide through by y times y plus 11. But we have to remember that y equals 0 and y equals negative 11 can be roots. Whenever you divide by polynomial, you always have to remember that the polynomial you're dividing by can be 0, and therefore, since this is the original equation, these two can be roots, but we doubt that they're the roots in question, but we still need to keep them in mind. So now we can rewrite this as 2 over y squared minus 36 plus 2 over y squared minus 64 equals 1. And now it only seems natural that we should substitute y squared equals z because there's no y term in it. There's only y squared. And now we have 2 over z minus 36 plus 2 over z minus 64 equals 1. So looking at this equation, we want to multiply through by z minus 36 times z minus 64. So when we do this, we get 2 times z minus 64 plus 2 times z minus 36 equals z minus 36 times z minus 64. And now we have to expand everything out and simplify. So over here we'll get a 4z term minus 200. And here we'll get a z squared minus 100z plus 36 times 64. And 64 times 36, that is 4, carry the 2, 384. 64 times 3 is 192. So we get 4, 0, 1, 9 plus 3, that's 2, 304. And then, so when we simplify, we get z squared minus 104z plus 2,504. And looking at this, it's easy to see that we just use the quadratic formula to find z. And using the quadratic formula, we get z equals 104 plus or minus square root of 104 squared minus 4 times 2,504 over 2. And then we try to simplify the stuff under the radical. Let's first factor out 4 squared if possible. 104 divided by 4 is 26, so we have a 26 squared. And then 2,504 divided by 4 is 6, carry the 1, 2, 626. So over 2. So we can remove the 4 from the square root and get z equals 104 plus or minus 4 over 26 squared is 676. Subtract the 626, we get a 50 over 2. And this can be written as z equals 52 plus or minus a 2 times root 50 is 5 root 2. So we figured out z, but notice that if z is bigger, the bigger z is, the bigger y is, and the bigger y is, the bigger x is. So we want to choose the larger possible value of z, which is z equals 52 plus 10 root 2. Now all we have to do is reverse our steps and try to get the root in this form right here. So now we have to convert from z to y, and given that y squared equals z, y is equal to plus or minus the square root of z. But as we said, the bigger that y is, the bigger x will be. So obviously we want to choose the positive square root. So y is going to be the square root of 52 plus 10 root 2. But remember from earlier, we found out from that two roots of this equation were y equals 0 and negative 11, but these are clearly less than this number, so we can completely disregard them now. And now we just have to add back the 11 that we got from substituting the y in for x. So we have x equals 11 plus square root of 52 plus 10 root 2. And now we have to make sure it's in the proper form that they're asking us. A plus a square root of an integer plus the square root of an integer. So we need to change this. We need to move the 10 inside the radical, and 10 squared times 2, that's root 200. So our answer is 11 plus 52 plus 200. That gives us 263. Anyway, thank you for watching, and if you found this video helpful, please leave a like and subscribe.